will continue with the lecture on concrete. We have looked until now at different applications of concrete, and in the last lecture we looked at the important components of concrete. We saw how concrete is made of aggregates, the space between the aggregates are filled with hydrated cement paste, and this cement paste is generally made of cement and water, but in most cases in high performance concretes, in better quality concretes, we have a mineral admixture that is added to the cement. This gives better properties in terms of the hardened concrete, improving the strength and the durability. We also saw that when mineral admixtures are added, some of these concretes become more cohesive, sticky, and therefore the workability could be affected, and we mentioned that superplasticizers are added to make the concrete flow better. We will see more about chemical admixtures in this lecture, and we will start looking at the different properties of the hardened concrete and what are the important aspects that we have to remember when we talk about concrete. In this picture we have a self compacting concrete being poured for a slab on grade, and if you have seen normal concrete and have not seen self compacting concrete, you would be surprised that concrete can flow as such. Here it is flowing almost a couple of meters in diameter and moving quite easily on a flat surface and through the reinforcement mesh. This is achieved by adding appropriate type and quantity of mineral admixtures as well as superplasticizers and viscosity modifying agents, which are chemical admixtures that we will discuss in a minute. Chemical admixtures are materials that are soluble in water. They are added in very small quantities, less than 5% of cement weight. Now these chemical admixtures are very common, and we can say that any high quality concrete made today has some chemical admixture in it. About 90 to 95% of concrete produced in several countries have some type of chemical admixture. Also, when we have high performance concrete like high strength concrete, we already discussed the case of silica fume concrete, self compacting concrete, we cannot make these concretes without chemical admixtures. Chemical admixtures can be put into different classes. First is the class of admixtures that affect the fresh state of the concrete. These are basically two types: water reducing agents and superplasticizers. Both of these reduce the amount of water needed for increasing workability. That is, when you have an application, when you have a very congested reinforcement or slender element that would need a lot of vibration, which is not possible, we need higher workability and we do not want to increase the water content. If we increase the water content, we will have lower strength and lower durability, which we do not want. Then we go to a water reducing agent or a superplasticizer and we get better workability. I think I made a mistake, right? Yeah. So, first class of chemical admixtures is the chemical admixtures that affect the fresh state. These are two types: water reducing agents and superplasticizers. These admixtures, no, but I think here there is a mistake, right? Yeah, I know, but reduce the amount of water needed for increasing. Okay, yeah. So I am switching. Okay, so we will start again. So the first class of chemical admixtures are those that affect the fresh state, and here we have water reducing agents and superplasticizers. These reduce the amount of water needed for increasing workability. So, suppose you want higher workability because of congested reinforcement, slender elements and places which cannot be vibrated well, then without increasing the amount of water we can have higher workability when we add a water reducer or a superplasticizer. On the other hand, if we have the same water content in two different concretes, but one has a superplasticizer or a water reducing agent, you will end up having much higher workability. Therefore, again we can increase the workability without changing the water content, and in some cases for the given workability we can reduce water, so that will increase the strength and the durability. So, the main purpose of using these admixtures is that we reduce the amount of water needed for a certain workability, therefore, we can increase the strength and durability, and on the other hand we can push durability to high levels without segregation, without the other problems of having to do with just more water content. Another set of admixtures affect the setting stage. They are set accelerators or set retarders. So, this can reduce or increase the initial rate of reaction between the cement and water. They can slow down the initial rate of reaction or increase, make the rate of reaction go faster, and this can cause a reduction or increase in the time taken by the mortar or concrete to pass from the plastic state to a solid state. Suppose we want setting to occur very fast, say in the case of shotcrete, where we shoot the concrete onto a surface, the concrete has to stick there and not fall off, or we have a case where it is a very cold temperature and we want the concrete to act very fast and not set very slowly, or we are in a hurry to finish a certain type of structure, we can use a set accelerator. Setting is faster and the reactions occur faster. On the other hand, if we want to maintain concrete fluid for a long period of time, we have a long duration of transportation, or we want the concrete to sit there and wait for the time when we are ready for placing, then we use a set retarder, which also comes in handy when the temperature of the environment or the ambient temperature is very high, which would already accelerate the reactions. That is compensated by using a set retarder. There are admixtures which affect the hardening state also, which can accelerate the development of early strength. Suppose we want a very early 3-day or 7-day strength, a hardening accelerator could be used. Another class of admixtures not very common in most of India is an air entraining agent. When we have freezing and thawing cycles in concrete, the water that is in the capillary pores expands as it freezes, or even before freezing it will tend to expand and move in the capillary pores, and if there is not enough space for free expansion, this expansion could lead to cracking of the concrete because of the expansive forces of the water becoming ice, and therefore, to compensate this, air entraining agents are used to create a set of uniformly distributed microscopic bubbles of air in the concrete or mortar. This provides space where the water can expand and become ice, and these bubbles remain even after hardening, and consequently we get higher freeze thaw resistance. There are also several other special purpose admixtures like shrinkage reducing admixtures, which are glycol based. They reduce the surface tension of the pore water, and therefore, there are less capillary stresses when water is released by evaporation or by hydration. There are admixtures which reduce the alkali aggregate expansion. There are corrosion inhibitors which prevent corrosion from occurring very easily. They increase either the chloride threshold or prevent the corrosion process from happening, they cut the electrochemical process from happening. Viscosity modifying agents or anti washout agents are used a lot in self compacting concrete, because there we want the concrete to flow without segregation, we need a concrete that is very sticky. It is also used a lot in underwater concreting, where concrete is poured underwater and we do not want the concrete to be washed away. Other special purpose admixtures not used very often are fungicides, water repellents mixed into the concrete. Multifunctional admixtures are where you have admixtures that have more than one purpose. They act maybe as a shrinkage reducing admixture and also a superplasticizer and so on. Why do we use admixtures in concrete? I have mentioned some of the advantages. We have more demands on concrete of the society and construction sector. We have to do better, the concrete has to do better, and this cannot be achieved without chemical admixtures in most cases. We need also to provide stability. When we talk about shrinkage, we talk about durability and so on. We want the concrete to be stable under certain environmental conditions, some of them may be quite severe. We also want to increase productivity and efficiency during fabrication, transportation and placing. For example, better workability, better maintenance of workability and so on. And in all these and other cases, the capacity of a traditional material, that is just a pure mix of cement, water and stone, is not enough to satisfy these demands. That is why we see more mineral admixtures being used and chemical admixtures being used in concrete. And this is a trend that we will see continuing, and most of the advances in concrete technology are coming about because of the use of mineral admixtures and chemical admixtures, the right type and the right dosage. Let us look at the properties of concrete, starting with the fresh state. What do we require in concrete when it is fresh, when it is still in the semi solid or semi liquid form? We want the concrete to be mixable, it should be easy to mix and transport, it should become uniform, there should not be non-uniformity within a batch or between batches, so that we have a consistent performance in the concrete and everywhere the composition is the same. The concrete should be able to fill the formwork, the molds completely without leaving any voids, and we should be able to place and compact fully without very high energy requirement, because that would mean that there would be errors and less energy used could lead to poor compaction. This is something that we would like to avoid. So, a concrete should be easy to place and compact without very high energy requirements, and ideally it would be nice to have a concrete which does not need any energy requirement for compaction. This is achieved to some extent by self compacting concrete. We also would like to avoid segregation during placing and consolidation. Segregation is the separation of phases within the concrete, where we would have maybe water and cement on one side and the aggregates on the other side, or the aggregates settling within the concrete. This is called segregation. We do not want to have segregation in the fresh state, and proper mix design and combination of the constituents will lead to this absence of segregation. Finally, we want the concrete to be finished properly, that the surface should be easy to make plain and give the texture that is required. These are some of the requirements of in the fresh state. What are the factors that can affect the workability of the fresh concrete? Workability is the ability to place, to finish and to compact the concrete. Water obviously helps, increase in water content increases workability. However, higher water content means that strength goes down. If you remember, when we talked about the microstructure, we saw that more water gives rise to more capillary porosity, more voids within the microstructure of the hydrated cement paste, therefore, we do not want too much water. Also, water increases the possibility of chemicals to enter, water to enter in the hydrated concrete, and this could lead to durability issues. In the fresh state, excess water can lead to segregation. So, even in self compacting concrete, which you saw in the leader slide, which showed high flowing ability, you have limited water, because more water always leads to more segregation. So, water content helps in workability, but it is not something that we always use for getting the workability that we want. Increase in cement content increases workability, because more paste means the concrete can flow more easily. However, again excess cement paste can lead to over cohesive sticky mixes, not to talk about the additional cost. Shrinkage, thermal stresses will also increase when we have higher cement contents. In terms of the other components other than the cement and water, the type of aggregate or the shape of aggregate will also affect the workability. Use of finer or more angular shape aggregates will need to higher water demand, and if this higher water demand is not there, then the workability drops. For the same workability, if your aggregates instead of being rounder are more angular, that means more water or cement paste would be required for the same workability. In terms of mineral admixtures, depending on the type of mineral admixtures, we will have different workability. Generally the mineral admixtures are fine materials, therefore they increase the cohesiveness of the concrete. The concrete has less bleeding, however it becomes more sticky. We saw that in the case of fly ash, due to the spherical nature of the fly ash particles, you have a ball bearing effect and therefore the flow is better, whereas in the case of silica fume, since the particles are very fine, you have to go for higher slumps in order to compact a structural element properly. Chemical admixtures can affect workability in the way that we want, depending on the type and dosage. If you have a superplasticizer, we already saw that workability is positively affected. We increase the workability for the same water content, or we can have higher water workability and decrease the water content when you add a chemical admixture. On the other hand, if you have an accelerator, the workability is cut very fast because the concrete starts setting and hardening quickly. So, depending on the chemical admixtures type and dosage, we can affect the workability in the way that we want. We talked in several cases about bleeding. So, bleeding in placed concrete is the settling of aggregates during the consolidation due to compaction or by gravity. This forces the excess water upward, and along with this water some cement is also dragged upward. So, this leads to a top surface which is called latence, and this sometimes you see on the surface of hardened concrete. You will see a shiny surface at the top which is rich in paste or water, that is called latence. There is accumulation of bleed water below reinforcing bars and coarse aggregates also. As the water moves upward, it meets obstacles in the form of coarse aggregates and reinforcement bars, and if the compaction time is not sufficient or the energy is not sufficient, this water stays below the reinforcement bars and the coarse aggregates, obviously leading to lower bonding and weaker interfaces. That is what is shown here in this picture. You have the latence here at the top surface, the bleed water goes up, rises to the top and forms this weak surface at the top. So, this weak surface will obviously not have much abrasion resistance and will be of poorer quality than the rest of the concrete. More importantly, we find that there could be an accumulation of bleed water along the bottom of the coarse aggregate or below the reinforcement bars. Obviously, this cuts the bond between the reinforcement bar and the hydrated cement paste, and in the case of the aggregate we have a weak interface zone. So, this is something which really we do not want to have through the concrete. Use of properly designed concrete, use of mineral admixtures decreases the bleeding. The only positive thing about bleeding is that as bleed water rises to the top, if there is a lot of evaporation, then this bleed water is removed instead of water being pulled out of the concrete. So, if the curing is bad and you have a weather condition where you have a lot of evaporation occurring, bleed water helps because it protects the rest of the concrete. However, it is not an excuse for doing bad concrete and encouraging bleeding. Curing is the best option to avoid shrinkage, cracking and so on. Let us move on to the response of hardened concrete, and let us look at some of the important features of hardened concrete. As we saw, concrete is a mix of aggregates and cement paste. The aggregate forms the skeleton and the voids and the interfaces are filled with cement paste. Aggregates generally will behave in a relatively rigid manner. In most concrete, the aggregate will not fail or reach stresses close to getting damaged. So, it behaves in an elastic manner. So, this would be the stress strain behavior of concrete in usage. The cement paste on the other hand varies in properties. The cement paste on the other hand varies in properties, and it could have much less stiffness and also a non-linear behavior. Concrete shows a composite response, something between that of aggregate and cement paste, and depending on the amount of aggregate we have a behavior that is closer to the aggregate initially, followed by a non-linear response. So, concrete is a composite response that is derived from the response of the aggregates and that of the cement paste. What is interesting is that concrete has initially a linear elastic response, followed by a non-linear response, the peak load and softening. Remember, when we talked about the response of materials to stress, we saw that materials such as concrete, rock and so on have this softening type response. Initially there is no cracking within the concrete, then micro cracks start to form, maybe in the interfaces between the aggregate and the mortar or the cement paste. These cracks start linking up, they reach a certain point when the concrete cannot take any further load, the cracks develop, leading to a decrease in the load carrying capacity, and therefore you have this softening. Even in cement paste they would be softening, but now this is changed to a certain extent. We do not have the same drop in load that you would see in cement paste, because the aggregates now are a combination of the concrete now is a combination of aggregates and cement paste. If we compare the response of cement concrete or Portland cement concrete to asphalt concrete that we saw in the previous lecture, we have sort of a similar response in the sense that there is an elastic part, there is a peak and then there is a drop. But if we put both these concretes on the same graph, we find that the strength of Portland cement concrete will be much higher than in asphalt concrete. However, the strains that the material can undergo are much higher in asphalt concrete than Portland cement concrete. Portland cement concrete is much more brittle and much stronger than asphalt concrete. Otherwise, there is a lot of similarity in behavior. In both the cases we have the material made up of aggregates, pieces of stone, the binder that fills the voids and the interfaces is bitumen in the case of asphalt concrete, and is hydrated cement paste in the case of Portland cement concrete. So, if we look at the how failure occurs under compression, I have discussed this a little bit in the previous slide. Initially there is an elastic response. This is now looking at the axial stress strain diagram. Some bond cracks form in the defects on the aggregate cement paste interface. These cracks start growing, they connect with more bond cracks or cracks start forming in the matrix. There is a faster growth of the matrix cracks, and finally you have the peak load followed by softening. Until about 50-60% you have primarily elastic behavior. This is where we want to be during service loading. During the usage of a structure we would like to be in this range. we ensure in design that we do not go into the nonlinear range during service conditions. Only during failure we anticipate that concrete can go to failure and beyond. When we do a test in the lab, we would find that at this point we would have some cracks in the specimen, and afterwards if we can control the test such that we have the softening branch obtained in a stable manner, we will see these cracks develop further, will connect, and we have failure in the form of a cone at each end occurring. This is say a cylinder which has been loaded in uniaxial compression, we would have the cones occurring here at the top and the bottom, and we have some vertical cracking and disintegration of the concrete over the middle. This stress strain response varies from one concrete to the other, and we find that as the concrete grade increases or the concrete strength increases, we find some typical aspects that change. First of all, we find that as the strength increases, say from a 20 megapascal concrete to an 80 megapascal concrete, the initial slope increases but not in the same rate. There is a higher initial slope but not proportional to the strength. However, the linear elastic slope or the elastic modulus increases with strength. So, you get a stiffer concrete as the concrete strength increases. We have a longer linear part for the higher strength concretes, because we have eliminated the defects, the interface is stronger, we do not have so much of micro cracking before the peak load. The linear range is relatively more in a higher strength concrete than in a lower strength concrete. In the lower strength concrete you see more of non-linearity occurring much ahead of the peak than in a higher strength concrete. So, you can utilize more of the linear part in a higher strength concrete than in a lower strength concrete. Obviously, the peak load is much higher because the strength is higher. You find that failure strains are almost similar, about 2000 microstrains is where failure occurs, and little bit more in the case of higher strength concretes. What is very important is that which happens after the peak. When you observe the stress strain curves of lower strength concrete, we find that there is a gradual drop in load carrying capacity, there is a gradual drop in stress, and what we see is that when we have higher strength concrete, there is a very sharp drop in the stress. That means the material fails in a very brittle manner, there is not much load carrying capacity once the peak is reached, and the specimen or the concrete fails in a sudden manner. That means higher strength concrete, this is something that we discussed in the previous lecture, higher strength concrete is much more brittle than lower strength concrete. So, we have to take this into account in design, and we have to use the proper stress strain diagram in design in order to represent this change in behavior as the strength increases. Another important aspect which governs structural design and how concrete fails is what happens to the transversal strain and the volumetric strain. So, in the stress strain diagram, now if we have an axially loaded case, say we have a cylinder under uniaxial compression loading, and we look at the axial compressive stress, this would be the curve. The stress increases as the strain increases, we pass the linear part, we enter into a non-linear part, and then the peak. Now, if we look at the lateral strain or the transversal strain, we find again that there is a linear part, and then beyond a certain point there is a very large increase in the lateral strain. Beyond a certain point, sigma sub a, which is limiting axial stress, the lateral strain increases very rapidly beyond a certain point. This is because cracks develop, and these cracks now mostly are oriented along the direction of loading. So, they open in the transverse direction. So, the strain in this direction increases very much after the point after the stress where the cracks develop. So, this means that volumetric strain, which is increasing if we consider compression to be positive, the volume is decreasing, then suddenly the volume starts increasing when the axial strain continues to increase. That is, as the loading increases, we find that the volumetric strain now is decreasing or the volume is increasing. Even though you are compressing it, the volume increases beyond a certain stress, and this is because of the dilation or the cracks opening up, which is creating a bulging effect in the middle under uniaxial compressive stress. There is a bulging due to the cracking, which is called dilation or lateral expansion of the concrete. And this is something that is very typical of what occurs in concrete close to failure under compression. If we can hold this from occurring, if we can stop the lateral expansion from occurring, then we can increase the effective load carrying capacity of the element, and this is where stirrups and ties that we use in compression comes in handy. We can understand this better when we look at the effect of confining stress on the normal stress and axial strain behavior. So, these are graphs from the book of Van Meer showing the normal stress versus the axial strain for different confining stresses. If you do not have any confining stress, this would be the stress strain behavior, failure occurring at an axial stress of say about 30 megapascal. The same concrete now with about 3 megapascal confining stress goes from here to here, 10 megapascal, 25, 50, 100. So, what we find is as confinement increases, we are preventing this lateral expansion from occurring, the dilation from occurring, we are preventing this increase in volumetric strain, and therefore, we have a higher load carrying capacity because the lateral expansion is prevented. So, the load carrying capacity goes up, and also we find the ductility goes up. The concrete, instead of opening up very easily under load, the cracks do not open up, and therefore, we have higher ductility. So, we find that when we look at the stress strain behavior under confinement, as the lateral confinement increases, the effective strength or load carrying capacity as well as the ductility of the concrete increase. However, we should keep in mind that this effectiveness of the confinement is lower for higher strength concretes. Why? Because higher strength concrete will have less cracking, and in the pre-peak we saw that higher strength concrete had a higher linear part, relatively larger linear range, and therefore less cracking develops, and if there is less cracking, there is going to be less lateral expansion, and the effect of the confinement comes in only when the concrete is prone to lateral expansion under high stresses. So, in higher strength concretes, the effectiveness of confinement, either active or passive through reinforcement, is less than in lower strength concretes. We looked at the Mohr-Coulomb failure conditions when we looked at failure theories. This is applicable to some extent to concrete. It is not exactly true for concrete, but to some extent we use it because it is a convenient way of representing failure under multi-axial stresses. So, here we have the envelope that could be used for concrete, and these different Mohr circles are for different types of loading. This is for triaxial compression, this is for uniaxial tension, and so on. So, from different triaxial tests, these Mohr circles at failure could be developed, and the envelope gives the failure surface for concrete. So, in many cases when finite element analysis is done, such type of diagrams are used to represent failure under multi-axial stresses in concrete. We have discussed fatigue earlier. Now in concrete also it is quite critical, because concrete structures can be subjected to a large spectrum of fatigue loads. In the case of earthquakes, we have low cycle fatigues. The number of cycles are less, but the amplitudes can be very high in an earthquake. Due to traffic loading, we can have high cycle fatigue, say in airport pavements, bridges, road pavements, concrete railroad ties or sleepers. We can have high cycle fatigue, where the element undergoes say a million cycles or so of loading. Very high number of cycles have to be endured when a structure is say subjected to sea waves, or in mass transit structures, say in metro rail, in elevated rail structures, we have even much higher number of cycles that the structure has to endure. So depending on the application, we see that fatigue becomes important in some types of application, and we have to take that into account. As in the cases that we discussed earlier, even in concrete we use the SN diagram or the Wöhler curve, where we have plotted on the y axis the relative stress level, one being the monotonic static failure strength, and on the x axis we have the number of cycles to failure or the fatigue life, and the cycling is done from a certain small minimum stress to the stress that we have plotted in this diagram, and we will get a curve from the different data points. We have this mean curve here and the 5% dispersion, where the bottom curve gives a safety or a risk of not more than 5% of the data being above this being below this curve. This 5% curve gives a risk of having not more than 5% of the data points below this curve. So this could be relatively safe for taking into design, and depending on the number of cycles that the structure is going to endure, we can now use this curve to go to this curve and then take off the stress level that can be applied, so that we do not have failure under fatigue. Say if we have a case where the structure has to endure 10 to the power of 5 number of cycles to failure, then we can go to this graph and get the value that we can apply in terms of stress. So we would say that not more than 65% of the failure strength can be used in design. So as long as this S max, the maximum stress, does not go beyond 65% of the strength, then the structure can endure 10 to the power of 5 cycles. And we will find that if the fatigue life is less, we can use more and more of the strength, and vice versa. If the fatigue life has to be more, then we have to use less load carrying capacity or less design strength, so that the structure can survive. Most concrete structures have steel in them. There is reinforcement in most structures. So we have to understand how stresses are transferred between the steel and the concrete, and we have to understand how failure could occur in the bond of the reinforcing bars. So these are different aspects that are important. Generally, concrete reinforcement bond will fail due to splitting of the cover and cracks developing from the lugs or the corrugations of the bar. We can have cracks going like this from the corrugation as the bar is being pulled. So this leads to cracking and finally failure of the cover or the concrete around it. So if you have a small piece of concrete with a piece of reinforcement embedded and the reinforcement is pulled out, you can have cracks developing like this. So, this could represent what will happen in the cover. If the concrete surrounds the steel properly, then you have some sort of confining effect, because as the steel is being pulled out, it will push the concrete apart. This pushing of the concrete is counteracted by the confining effect of the concrete, and then the pull out strength increases. It is not so easy to pull out. A similar effect forms due to the wedging forces of these ribs. As the steel is being pulled out, the concrete resists the movement of these ribs, and therefore you get a wedging action, and this again resists the pull out. So, between these different mechanisms, the pull out of the reinforcement is prevented, and there is a good bond leading to stress transfer between the steel and the concrete. So, these are different aspects that we have to keep in mind when we consider the failure pattern or how reinforced concrete fails. We also have to understand that there is a reason for modeling concrete failure. We have to understand the constitutive relations for concrete, because for structural analysis we have to predict how a structure behaves, and for that we have to know the material properties. We have to understand how the plain concrete behaves, we have to know the stress strain behavior of the plain concrete, we have to obviously know how steel behaves and what is the interaction between the steel and the concrete, that is the slip behavior, and if there are cracks in the concrete, what will happen to the cracks. So, only when we understand all these different aspects, which brings in material science, materials engineering and structural analysis, we will be able to predict what will happen to a structure, and we will have to finally check if the simulation meets the actual behavior through some amount of testing. This is how structural analysis codes and practices are developed. The modeling of concrete failure is also important when we have to develop new materials or we have to validate advances in material science. Here, when we have a certain material, we want to make this material better, we have to simulate numerically or analytically how this material behaves, and therefore we can understand how the constituents change the material behavior, so that we can reach a better material or better modeling of the material. We want to simulate what would happen in a test, but we would want to avoid a lot of testing, so that we can go faster in terms of material development. For this again we have to go one scale lower, we have to understand how hardened cement paste behaves, we have to know the stress strain behavior of the cement paste, of the aggregate, of the interface. It is not very clear now how the interface is defined. We have to look at a definition of the interface, we have to understand how we will represent the interface and how we will model the interface. Again micro cracking, it is not very clear how we will do it. There is a lot of research going on in these aspects. So, modeling of concrete behavior through proper understanding is important for structural analysis as well as material science when we want to develop better concretes. We will finish this part of the lecture talking about time dependent effects in terms of shrinkage and creep. Now, shrinkage and creep are both strains which occur over a long period of time, and both involve the movement of water. Shrinkage occurs when water is lost to the outside or to the environment, or it is consumed by the hydration reactions. Creep occurs when water is forced to move by stress. Water in the capillaries is forced to move when we apply a constant stress. Both these strains are not completely recoverable when the load is removed or the concrete is re-wetted or resaturated. Part of it, however, can be recovered. And both these are important because we do not want the dimensions of a concrete structure to change during service due to drying or the applied load. This could lead to cracking, this could lead to excess deformations. To understand shrinkage and creep, we have to see what are the different ways that it can occur and how it occurs. In this diagram, we have on the y axis the axial strain, in an element that is either drying or subjected to axial stress, and on the y axis we have time in days. Suppose we cure the concrete for a certain amount of time and then allow it to dry, we have this curve corresponding to shrinkage, free shrinkage. After some time, say if we re-wet the concrete, we saturate the concrete, then it will swell again, it will absorb water and swell, but it does not go back to 0 or the initial state. So, there is a partial recovery, but not complete. Now, if we were to take a concrete, not allow it to dry, but we load it, such that we apply a sudden load and keep the load constant, then there will be a sudden increase in strain, which is the instantaneous strain proportional to the Young's modulus, and then what we will find is the strain does not remain constant, but it keeps increasing slightly. We saw such behavior when we discussed viscoelastic materials. This is called the basic creep. When we remove the load, some part will be recovered in addition to the instantaneous part, and this recovery is slow, but it does not reach the initial position. If we have both creep and shrinkage occurring, then we will find that the observed total strain is much higher. This would be the sum of basic creep and free shrinkage. Additionally, there is a drying creep component. So, the actual creep is more than the sum of just the basic creep and the free shrinkage. This is due to an additional phenomena called drying creep. So, this would be how the curve looks, and now if we remove the load and resaturate the specimen, we have an elastic recovery, then a creep recovery, but again we do not go back to 0. So, we find that we can have significant changes in the deformation of a structure as the load is applied, ambient conditions change, and this is something that we have to design for and we have to prevent as much as possible. What are some of the effects of shrinkage and creep? Axial strains increase with time. For example, we have columns under compressive loads, bridge piers. So, here we will find that the axial strains will increase with time. This is important because columns in a bridge or bridge piers could be of different lengths or heights. So, each of these will have a different displacement and could make the deck be displaced non-uniformly. And also, if you have large displacements of columns, then it can lead to cracking in the other complementary structural elements in the structure. Deflections will increase. If you have a beam or a girder under flexure, the deflections will increase over time. Again, it could lead to serviceability issues, and which we would like to prevent. Stress relaxation occurs, that means the stress drops due to this increase in strain. That means if you have a pre-stressed concrete element, the pre-stressing force decreases as concrete shrinks and creeps, because the pre-stressing force is applied by stretching a cable and anchoring to the ends of a beam, and if these ends move closer to each other due to shrinkage and creep, the pre-stressing force decreases. Cracks occur also in elements that are restrained due to the tensile stresses that develop. For example, a pavement or a slab on grade where the bottom is not moving that much due to shrinkage, the top surface is exposed, shrinks more, then you have tensile stresses that develop at the top leading to cracking. So, these are some of the effects of shrinkage and creep, and that is the reason why we are concerned about it. There are different types of shrinkage that I will rush through, which we will have to remember. There are different types of shrinkage that we will look at briefly and quickly. This is important for us to understand as the type of concrete changes, some of these mechanisms become more important and others become less important, and therefore, it is good to know the different mechanisms of shrinkage. Plastic shrinkage is that which occurs in the plastic state when the concrete is still wet. This we will find more in the case of high strength concretes which have mineral admixtures like silica fume and fly ash, therefore, curing is very important. Autogenous shrinkage is the sum of chemical shrinkage, where the volume of the hydration products of cement and water is lower than the sum of the volumes of the cement and water. Self desiccation is where you have a reduction in the pore water due to hydration. As the water is consumed by the cement, the pore water decreases. The sum of chemical shrinkage and self desiccation is autogenous shrinkage, and this could be quite high in cement paste. So, it is of importance when you have very high cement contents in the concrete and could lead to significant shrinkage. Thermal contraction or thermal shrinkage is where you have very high temperatures due to the exothermic reactions in a mass concrete or a concrete with very high cement paste content, and then afterwards the concrete posterior to setting will drop to reach equilibrium with the environment and contracts. This again is significant in mass elements and in the cases of high cement contents. More classical is drying shrinkage, basically occurring in poorer concretes, lower grade concretes, where the loss of water can be high, leading to lot of drying shrinkage. In high strength concretes, good quality concretes, we will find that drying shrinkage is less. Also less will be carbonation shrinkage, which occurs when carbon dioxide enters into the concrete, reacts with the calcium hydroxide, and consequently we have volume reduction, loss of moisture and cracking. This again will be less in higher quality concretes which are more impermeable to air and carbon dioxide. What happens due to creep? This is something that has been observed since the 1960s. These are the famous Rush curves, where we see that if a load is maintained for a certain amount of time, the strain increases. So, here you have curves of tests done at different loading rates. This is an instantaneous test, this is the stress strain behavior when the test is done very fast, then this is at 20 minutes, test taking about 100 minutes. All of these are uniaxial compression tests. This is a test taking 7 days, very slow loading, and this is theoretically what will happen if the curve, if the test under uniaxial compression takes infinite time. Failure occurs at different points for each of these loading rates. If we join this, this is called the failure limit, and what we find is slower the loading rate, less will be the stress at failure. When we load very fast, the stress is say at this point, and when we load very slowly, say a test running about 7 days, will fail at 80% of the load that we got for a test run at 20 minutes. And if on this 20-minute curve we hold the load constant, when the strain reaches the failure limit, then failure occurs. So, this is now creep loading. We load at a certain loading rate and then keep the load constant. Then now the strain increases due to creep. When the strain reaches this envelope of failure limit, failure occurs. Only when the stress applied is less than about 70 or 60%, you find that the strain will never reach the failure limit, and therefore failure will not occur due to creep. And you find that as long as you are above this, how does the creep limit come in? I forgot. We find that the strains will keep increasing until we reach this creep limit. This will be the maximum strain that will occur in under a certain load. So, that is defined by the creep limit, and this is the reason why we keep stresses under service loads to be less than say about 60% of the strength, so that we do not reach failure and we do not have excessive strains due to creep loading. Creep is therefore a gradual increase in strain due to applied load, and it is defined in terms of time dependent strains under sustained loading. When concrete is restrained, creep occurs as relaxation or lowering of the stress, that is, if we keep the strain constant, the load drops or the stress relaxes. Types of creep, basically two: basic creep, when there is no loss of moisture to the environment, there is creep without any loss of moisture to the environment, only load is applied, no drying is occurring. Drying creep is the additional creep due to the effect of drying, that is the total creep minus the basic creep. Here you have the effect of both drying and creep. Creep recovery is when the load is removed and there is a instantaneous decrease in strain followed by a gradual decrease, which is called the creep recovery, and this is what you see here. When you load a piece of concrete, there is an instantaneous strain and there is a creep strain which increases over time. When the load is removed, we have creep recovery, which is instantaneous, followed. When the load is removed, we have instantaneous recovery, which is very fast, followed by creep recovery, where we have part of the strains recovered, but finally we have a residual deformation that is not recovered. These are tests done by Neville on mortar under 15 megapascal stress, and then this was unloaded. We also have combined effects of shrinkage and creep, which are important. Creep strains are always opposed to the applied stress, that is, we will always have strains in the direction of the stress, along the direction of the stress, and these are additive to the elastic strains, that strain will always be in the direction of the elastic strain, and this will tend to increase the deformation beyond the elastic strain. Poisson ratio remains same in creep, that means lateral expansion will increase with creep. This is something that we have to remember, that lateral strains also will continue to increase due to creep. Shrinkage strains are volumetric, whereas we saw the creep strains occur in the direction of stress. Shrinkage strains are always volumetric, shrinkage will be the same in all directions. So, when we have creep and shrinkage occurring together under uniaxial loading, all of them will increase the axial shortening or axial strain, whereas in the lateral direction shrinkage and creep can compensate each other. In some cases, creep can also be beneficial, for example, in a slab on grade under conditions of restrained shrinkage, creep will lead to a decrease in the stress due to the relaxation. Say under restraint, this is the amount of tensile stress that is developed. This is now we are looking at stress on the y axis and time on the x axis. As the concrete shrinks and the bottom is restrained by the soil in a pavement or a slab on grade, the top will have tensile stresses developing due to the shrinkage, and cracks will occur when the stress exceeds the tensile strength. Over time now tensile strength is also evolving, the concrete is setting, it is hardening, so tensile strength is increasing. At a point where the tensile stress is higher than the tensile strength, then cracks will occur. But what happens due to creep? Due to creep, the stress induced is relaxed. Due to deformations, the effect of the confinement or the restraint, the effect of the restraint is decreased, and therefore the stress relaxes. The actual stress that is acting in tension is lower than that induced due to shrinkage. Due to creep, this stress now drops. So, that means we have more time for hardening to take place, and it is possible that the crack occurs much later or does not occur at all, because due to creep the stresses have relaxed and the actual stresses that are acting are much less. So, in some cases creep can be beneficial, especially when you have restrained shrinkage causing cracking. How do we get all these properties? We have to do tests for a long period of time, and this gives the scheme of the different tests that can be conducted on concrete to get the shrinkage and creep behavior. First of all, to look at the autogenous shrinkage, we have to take a completely sealed specimen and monitor what the strains, how the strains evolve. So, here we plot now strain on the y axis and time on the x axis, and deformation in a sealed specimen gives us the autogenous shrinkage. Suppose we have a cured specimen with only the sides exposed, that is drying is occurring. After curing, you will see that there is drying shrinkage occurring, which is in addition to the autogenous shrinkage. This is the total shrinkage, this would be the autogenous shrinkage, and this is the drying shrinkage. This we would do by measuring strains on a specimen where after curing the sides are exposed to a dry environment and we allow the concrete to dry. In similar specimens under load, we can get the basic creep and the drying creep. In the case of basic creep, what do? We allow the specimens to cure and then we suddenly apply a certain load and keep that load constant. So, we will have an instantaneous elastic strain and then there is a creep strain. In the sealed specimen, this strain which occurs in addition to the autogenous shrinkage is the sum of the instantaneous strain and creep strain. In a specimen that is drying and also subjected to load, we will have a curve given by this, where we will have an instantaneous strain and a higher creep strain. Now, this creep strain is a sum of basic creep as well as drying creep. So, this curve now in addition to the shrinkage will show us instantaneous strain plus basic creep plus drying creep. Okay. So, this looks very complex, but once you look at it for some time you will understand the different mechanisms all put together which can occur in concrete and how through testing over a long period of time, these tests last for at least 6 months to 1 year, we can quantify the different aspects of long term behavior. So, we have looked at chemical admixtures, we have looked at different aspects of mechanical behavior of concrete. In the next lecture, we look at durability, which is very important because we want our structures to not only perform well during service, but we want the service life to be long enough so that we can use the structures for a long time. So, we will look at durability in the next lecture. Thank you.